This is a quick walkthrough of practice activity 5 on dimensional reduction using principal component analysis um, here. So I've broken this notebook into a number of sections: section 0, section 1, section 2, section 3, and then the wrap up. Each section well, section 0, you have to run for all the sections. It just sets up our data here. Section 1 uses the iris data, looks at simple stuff with that. Section 2 looks at our cancer data set. And then section 3 looks at this new handwritten minced digit data set and that sort of stuff. So I've got the 3 sections broken up. You always have to run section 0, and then you can jump to any of the other sections and start there. But I usually just run all the cells when I get started anyway, so you might want to consider that. So let's just go through this. Section 1 does our setup, imports our libraries, and gives a quick overview of our data sets here. And again, the new one we'll be using is this Mintz handwritten one that we mentioned in the course, in this unit overview. Now, unit 1, we're going to look at the iris data set. Just load that up. Remember, now this has just 4 components, and we're just going to look at how principal component analysis can be used to visualize this data a little better. So again, we break our data up into X and a Y vector, our input and our output categories. But rather than just calling X and Y, since we have multiple data sets here, I'm calling the X iris and the Y iris here, and we'll use other names later on. So we have X iris and Y iris rather than just X and Y here. Now, to use principal component analysis here, up above we've done this import for principal component analysis, and it's called PCA is our little acronym for it, and then we'll use it here. So here's our code. We create a PCA system, and we specify the number of components. This is the number of dimensions we want. So we're going to reduce the iris data set, which is 4 features, down to 2 features here, 2 principal components. And so I'm just calling that, I got to give it some names, so I'm just calling it PCA2 to kind of link in with the 2 components. Now once I have that, I have to fit my data to it, so I say PCA2.fit transform, and I specify my data, which is usually X, but again now I'm using X iris because that's our, we have multiple data sets, multiple X's, so we're going to use X iris, which we created up here. And again, the result I'm calling X iris PCA2, just so I know I can look at both. X iris is the original data with 4 features, and X iris PCA2 is the new version with only 2 components here. And now I can plot those. Here's a scatter plot using the original X iris, and I just picked out 2 of the features. There's actually 4 features, but printed off those. And notice they're kind of messy. It's not a clear division here. Now, if we do principal component analysis here, so now we're printing off this X iris PCA2, and again, that's what we got from when we did our principal component analysis. So this will have 2 features. Okay, sorry for that interruption. So this X iris has 2 features, and so we're just plotting those 2 features here because we again said the number of components are 2. So we're going from the original 4 components down to just 2 components, and now we can plot those 2 components. And so it kind of one of the ideas is that it helps break the data up into a little cleaner format while retaining the useful information here. So here's your first task to describe this and how it works. And that's all we're doing with the iris data set, is just looking at that. Now in section 2, we're going to look at the breast cancer data set. Again, we're importing that. And remember now this, we have a diagnosis, either malignant or benign here. And then we have 30 different features. So rather than just 4, we have 30 different features here. So we're working with those. And again, so we're grabbing the X and the Y, the features, and then the categories here. So our categories are diagnosis, and the rest of the features 1 through 31 here are, and so rather than just calling X, we're calling this X cancer and Y cancer as our categories. Now we're going to scale this data. We've done this before, so we're just going to take the X data and scale it. so that rather than having numbers all over the place, like between up to 1,000 and other ones under 1, it'll scale it all uniformly. And now we're going to apply this principal component analysis here, and we're going to do it in a number of different ways. So again, every time we do a PCA system, we have to specify the number of components. So we're going to try looking at reducing, again, we have 30 components up here, 30 features. We're going to try to reduce that to 1 feature or 1 component, 3 components, and 5 components here. And so we have actually 3 different PCA systems that we're just labeling PCA 1, PCA 3, and PCA 5, and each one we're specifying different number of components. And then we're applying that to our cancer data. And remember, when we did our cancer data, it was called just X cancer here, up here when we grabbed it. And we're saving it, and so we're saving each of these results as X cancer PCA 1, X cancer PCA 2, 3, and 5, so we kind of keep track of each one. And now you're going to apply a couple algorithms. The first one is k nearest neighbor. Now we did something like this before. We did this with our original data. Now before we actually broke the data up into test and training data sets, but we're already working with different data sets here, so I decided not to do that. So we're not going to break the data up into test and training data sets, just to kind of keep this simple, because we already have 4 data sets here. We've got the original X cancer, and then we have each of these PCA versions, so I didn't want to get things too complicated. So here we're running this k nearest neighbor on our original X cancer data with our Y cancer, the labels here, and we're predicting a score. And now we're trying to just work with what if we reduce the 30 components down to just 1 component and predicting a score here. So now we're using our X cancer PCA 1, where up here again we use this to reduce this to only 1 component. And likewise, we're going to do this for 3 components and 5 components. And you see that it's your job to kind of look at these scores and notice this. Now, PCA may not necessarily be improving our scores, but what we want to see is that we can reduce the data significantly, the size of the data, and still get very good performance from our data. So rather than going from 30 features, we can cut this down quite a bit and see that we get still get quite good predictions. And the same is true, we'll do the same thing with support vector machines. So that was k nearest neighbor up here, and remember we also looked at support vector machines. And again, we'll be doing support vector machines on our original data, and with reduced to 1 component, and 3 components, and 5 components. And again, we'll see similar results where we can reduce the number of features significantly and still get relatively good prediction values for this. So your job here is to write this up, kind of analyze the score, and do a little write-up on that. Just answer these 3 questions for this. So do that for both k nearest neighbor up here and for support vector machines down here. Okay, now section 3, we introduce a new data set. This is the handwritten digits. It's called MINST, M-I-I-S-T. Here, these are 16 by 16 images, so there are 64 pixels in each one. So it's still really small, and so dimensional reduction is not going to help us that much here. When we get up to where this is more often used is like where you maybe have images that are 256 by 256 pixels, or 1,000 by 1,000 pixels. So you might have 1,000,000 dimensions here, and you'll do dimensional reduction with that. But those data sets are kind of hard to load in at this beginning stage, so we're just going to keep this relatively simple and do these simple images to start with, because we'll see some change here. So here we load in our data sets. The MINST data set is actually built into the sklearn library, so we can just load those in directly here. And here's some code that just displays them a little bit so we can see that. And now again, we're taking we're using X digit and Y digit as our input features and our output categories. So the idea is that for each of these, you'd classify this as a 0, this is a 1, this is a 2, 3, 4, etc. It's kind of hard to see here, but if you actually look at the data where we first have it, it's quite obvious to you as a human that this is a 4, this is a 5. Though some of them are a little more challenging than others. So okay, so what we want to do there in this section is we load in the information, we've set up our x and y there, and here I want you to try to find what is a good number of components for this. So from the 64 dimensions or features, how far can we reduce it and still get some good results? And we're going to only look at support vector machines here. So just look at support vector machines here. Now, again, reducing it all the way to from 64 to 3 probably is just too far, again, because we've got this, we see this dropping down to the prediction rate to 72. And you can actually show mathematically that although you start at 64 components here, you can drop the number of components to further and further without seeing a lot of decrease. But again, when we drop it all the way down to 3, we're seeing a big decrease. So this is just a mathematical amount of information here, but this isn't a curve that shows the actual prediction. So your job here again is to find a sweet spot in this idea. So how many components can you reduce this to and still get a good prediction rate? So can you without any compression, you should be predicting, support vector machine can probably predict almost 100% of these images. So again, we should be looking at, can we do 90 or 95%, and how low of number of components can we get? Can we get to 97% and still have significant reduction? So see if you can find a good balance where you can reduce the number of components and keep the prediction score relatively high, higher than 72 certainly. Okay, so that's your task 4. Task 5 is what I mentioned earlier, is this article where we want you to read this article about noise filtering and just give me a couple sentence summary of that. Okay, so that's an overview of principal components analysis and how it can be used for in Python to do some dimensional reduction.